All right, so without further ado, let's start. So we recap from where we left, as to say, the assembly of the mass matrix for the overall body. So we basically started off from the concept of kinetic energy of the overall body, which we denote by Ti, as basically just a sum over the number of the element Ne of the kinetic energy of the single element, of the single elements. This basically turned out to be quite a nice and convenient expressions, as basically we resorted to the fact that our kinetic energy of the element was referred to the overall set of the nodal quantities of the body, basically allowing us to put in evidence the sum sign only with respect to the mass matrix. Let's say thus rendering, I would say, very straightforward the procedure of assembly of the mass matrix. So this was basically defined as Mi Qi dot with Mi, which is the mass matrix of the overall body, being just the sum of the masses of the elements, like so. Okay, I will just rewrite it for the sake of clarity. So of the body. Okay. All right, but in terms of submatrices, what is the impact of this finding? Or if you want more straightforwardly, how do we pass from the submatrices of the element, submass matrices of the element, to the submatrices of the mass matrix of the body? And in this sense, how do we calculate and assemble the inertial shape integrals of the body, starting from the shape integrals for the elements? Well, it's actually quite straightforward. We're going to only see a couple of examples, and that's it. So for the case, of course, of the submatrix of the mass matrix of the body associated to translation, of course, the previous equation, let's say, assumes this form. So it's, I would say, kind of straightforward. And therefore, this basically becomes written in such a way where, of course, this is the mass of element J, and this instead is the mass of the overall body. Okay, so I would really say it's kind of trivial. It's more interesting to see what happens to the submatrix R theta, as this allows us again to see what happens to the inertial shape integrals of the overall body when we start off from the same quantity associated to the element. Okay. It's a little bit in the middle of the way. Right, so This is minus the integral over the volume of the element Vij, if you remember, or rho ij, ai, r over bar tilde ij, applied over g, I, in the Vij, okay? And this in turn could be written as such, if you remember, as C I, from this, basically from the distribution of this summation here, of course, on the density and on the quantity R over bar tilde, we can get that the first inertia shape integral of the overall body is just, again, the sum over J, the number of the element, of S, sorry, this is a vector. Yes, that's a vector of Ij psi. Okay, so again, we pass with a very kind of ease from the element to the overall body just by means of a sum. Okay, and this is basically the first inertia shape integral for the overall body. Okay, same thing. I will not go through it, otherwise it will take too much time. But the same really goes for what we have said: 3, 4, 5, and 6. That's to say, for all the other submatrices, we have that S, C, C, I, always KL, is just the sum, again, of J from 1 to N E of S, Ij, C, CKL. So these are the additional 6 inertia shape integrals. Okay, so again, this shows once more that the adoption of finite element model really also enables to pass from the element level to the overall body level in a quite simple way. So to assemble all of these quantities just through a sum operation. Okay. All right. So this is basically the end of yesterday's lecture. Today, what we're going to do is to, let's say, pose our attention to the stiffness matrix. And then, as I was mentioning, we will start an exercise dealing with 2D beam element. Okay, so let's try to put all of these concepts in practice. And let's try to start to derive the mass matrix and the stiffness matrix of a 2D beam element. Okay. All right. Okay. So here we go. So just to clarify, these are the additional six inertia shape integral. Okay, so, wow, you can't really see that much if I write in red here. Do you actually need this, or is it fine? Because you cannot see it that much when I write in red. Okay. Okay, so again, 7, as we have said yesterday, in total. All right. Now, we're going to see, as I was saying, is how to, let's say, derive the stiffness matrix. So, definition of the stiffness matrix. Let's say, at least as for the start, for the element. Okay, so we start always from the element level. And as we always have done so far, we start with the work of the elastic forces for the element J. So work of elastic forces of the element, J of body I. Of course, this is always the virtual work. So we going to consider the virtual work. And it has, of course, a superscript I and J as the opposite of the work done by elastic forces. So it's going to be Vij. Then we're going to have Cauchy stress tensor written in Voigt notation applied over the virtual variation of the deformation of the element epsilon ij. Integrated over the volume. So where this is, of course, the linear part of the Green-Lagrange strain tensor. Okay. If you want, I can specify it. So this is Cauchy. Oops. Cauchy stress in Voigt's notation. And this is Green-Lagrange strain, linearized, of course, the linear counterpart. The constitutive relationship is the following. It's basically here, we introduce it, it's Hooke's law. It's Hooke's law. So it's always linear, at least for us. Not in general, of course. And it's written like so. So it's basically, of course, sigma ij equal to C. Well, this is a matrix, in fact, of the constitutive law. When you have, in theory, you should connect two tensor of order 2. This should be a tensor of order 4. Since here we are dealing with vectors, this is a matrix. There is a difference between a tensor and a matrix. You should know it. So a matrix or a vector is a collection of numbers with no particular physical meaning. A tensor is a mathematical entity whose components change from one reference system to another according to a specific law. That's different. Huh? All right. So basically what we do is that we define our deformation epsilon ij as a differential operator D, linear differential operator. Basically, it's a derivative. Huh? Applied over what? The vector of deformation induced displacement. Okay. Let me just, yeah, which we didn't define as U, but we defined as, so let me just stress out. So this is a capital W, and it's the work, virtual work. Here we have a small w. If you remember, is small case w is the deformation-induced displacement at element level. Okay. All right. I will write it down in any case. So this is a linear differential operator. And this is the vector of deformation-induced displacement. Displacement at element level, because at body level it was U over bar, if you remember. So this is at element level. In fact, it has a J between the superscript. Okay. So with all of these pieces of information, we can write down at this point the work of the elastic forces for actually, let's introduce another piece of information. So from previous results, actually, all right. Let me just rewrite this in another way. Let me rewrite this in terms of U over bar ij. So this U over ij, what is it? It's the vector of deformation-induced displacement, so for the element, but described with respect to the body frame. Okay? So if you want, I can specify it here. We already have introduced it. So with respect to B1, B2, and B3. Okay? Is it clear? All right, so, all right. And so then let's write it here this way because it's easier if we do it like this. And this, we wrote it to be Nij B2I applied over QF I. Where, again, this QF is the vector of nodal quantities induced by deformation, the variation induced by the deformation expressed at body level, okay, for the overall body. This we define by definition, so to simplify it a little bit, as N over bar Ij applied over QFI. So we basically included these two parts into a single matrix, N over bar. Okay. If we exploit this fact, we can write down that epsilon ij, the vector of the deformation, is dij n over bar ij over q f I. All right. And therefore, it follows that our virtual work Bij S of external forces. I'm not sure if I had put also here the S. Yes, of course, yeah. Okay, it's fine. It reads, as we know, QF I transposed applied over K F F. In this case, we have Kij, and then, so it's a quadratic form, no, as usual. Where, okay, so we basically, now we substitute this expression in the previous work expression of the work that we have here at the very first page. So we substitute everything in here and we use the constitutive law. So to get this, since we have already seen that the final expression can be written as such, you can already identify this part here, which is integral over Vij of d ij n ij, all of this transposed C ij, which is the matrix of the constitutive law, it's the linear constitutive relation, Vij n over bar ij in the V ij. Okay, is it clear? I mean, I think it's, we have done it at body level as well. So again, we have, just to recap it, we have this expression of the virtual work. We have this constitutive law. We have this expression of the deformation. We have this expression of the displacement induced by the deformation. We put all of this together. We put it back in the first expression. And since we're going to have something of this sort, you can prove it by yourself if you don't believe me. Eventually, this K, results to be like this. And this is the structural stiffness matrix. Again, structural stiffness matrix for the element J. For the element J, yes. In fact, here I miss super important J superscript. Okay, again, it's the structural stiffness matrix. If you remember, so it's not the stiffness matrix, it's the structural stiffness matrix. What does it mean? What's the difference here? Again, if you remember, in this case, we only have the, let's say, the parameters which are associated, the variables which are associated to the deformation, okay? It means that there is no rigid motion here encompassed, okay? So what is the consequence of this? The consequence of this is that this matrix is not semi-definite positive, it's definitely positive, okay? Did you remember when we went through this part, So there is no rigid motion, so there is, for every kind of possible set of these vectors, which is a non-null vector, you're going to have accumulation of elastic energy, meaning that you are excluding rigid rotor translation. Yeah.
Nella formula del delta del lavoro virtuale, dovremmo avere il delta Q.
Delta Q. Certo. Yes, of course. I'm going to have it here. Should be here. Only one. Because this is the one associated to deformation. This is the one associated to stress. And when you have it here, so this is one comes from here, and it's the delta Q. The other one comes from here to this, to the constitutive, and so you have it. We have seen it already. But yes, you're correct, of course. Yes. So delta.
Sono entrambi IJ o...
No, they work in I. No, we remember that we define a vector, so only I. Okay. Thank you. So again, structural stiffness matrix, it's positive definite. So again, every kind of non-null vector that we apply, we consider for the element will be associated to a non-null strain energy. Okay. All right. So from here, as for the mass, we now assemble the stiffness matrix for the overall body, structural stiffness matrix. Okay. Well, there is not really much to say. We start from the same quantity, but for the overall body, as we went through the kinetic energy. So it's G, it's the dual, if you want. So it's the sum, again, from I to the number of elements of the virtual work associated with external forces, of course. For the element J. And therefore, this becomes equal to the sum from J going from 1 to NE. Actually, let's put it directly inside. So it's minus QITF, the sum of K FFIJ applied to delta QFI. Okay? And as you can see, also in this case, as it was for the mass matrix, it's super simple to assemble the structural stiffness matrix for the overall body because it's basically just a sum. Okay? So this is basically okay, and of course it means that KFFI is equal to the sum okay. So this is basically what we already established before actually diving into the finite element formulation. Now we see that the relation between this that we already saw and this that we have just derived is very simple for the case of finite element methods. Okay, so this is again the structural for the body I. Okay. Now the last part that we have to do is basically pass from this, which is the structural stiffness matrix, so for the overall body, to the structural matrix, the body. Let's do it. It's quite easy. So so if we define Qi, as we have already done, as R, if we consider, because we have already done it, if we consider and then we have theta I transposed, and then we have QF that we have just made use of, then we have that, again, the virtual work of external forces of the body I can be written as Qi transposed applied over Ki, and not Kff anymore, over delta Qi, with Ki is just, by definition, well, something that we have already encountered, which is this. Okay, and this is the stiffness matrix. For body I. Okay. Okay. Now, the idea is basically to implement all of this knowledge we have developed into a specific case, as we have done at the conclusion of every module that we have done. Okay? So in particular, to make things easier, we will implement all of these things into a 2D case, not in a 3D case, just for the ease of notation. Not there is no actually no conceptual, let's say, difference. Qua. Correct. Yes. True. Yeah. Thank you. Yeah. All right. So let's dive into this. But before actually doing this, let's see if we can specify again all of the quantities that we have seen for the 2D case. Okay. All right. So let's dive into this example. It's a 2D beam element. So the thesis, so what we want is to derive the mass matrix and the structural matrix for the element. Okay. Let's say prior doing this, let's specify some of the relationships that we have already derived for the 3D case into the 2D case, so that we can ease out our notation. So in so doing, we say that the position of a point of the element J in the body I with respect to the inertial frame can be written as, of course, Ri, then we have the matrix, general J, and P dot, so the velocity, which we will need, of course, to derive the mass matrix, therefore reads R dot I, and so far no big surprise. And this we're gonna have it as A theta, so the derivative of A with respect to theta. We already done it in the 2D case. R ij over bar theta dot I plus A n ij b2 I qf I dot. Okay. It follows that the expression of my mass matrix for the element J can read as such. Here we have, of course, as usual, an identity matrix. Here we have A theta I applied over R I j over bar. And here we have A I n I j b2. Okay, of course, these are basically the submatrices that we have to derive. Here we have Rij transposed applied over R Ij. And then here we're going to get R Ij A theta transposed Ij A I n Ij, and again B2. So basically, this is really nothing new with respect to what we have seen. Wait. Of course, this has to be the integral over Vij of the density Ij. And then we're going to have the last term here, which is B I 2 transposed n Ij transposed n Ij b2 I. Okay, and of course here everything is symmetric in the Vij. Okay. Where we have we consider that A theta I transposed apply over A, we call it I, the I matrix, tilde, with I tilde, which is a very simple matrix. In this case, is 0, -1, 1, 0. Okay, so we denote it like this. So basically, this part here, we can denote it as I, okay? So the inertia shape integrals can read, can I turn the page? Hmm? Questo? Thank you. Yes, of course. Yeah. So basically, the inertia shape integrals become as follows. So S ij c becomes the integral of Vij rho ij and ij. Okay. And this can be written very easily as such. Cij Okay. So this is the first. Then we have this one here. Applied over the integral over the volume Vij of the density psi ij transpose apply over I, and this is the vector that we were, let's say, defining before. Okay, and then there is the last one. So all of these quantities are just specific expressions to the 2D case, with respect to the 3D case that we saw already. So our task now is to introduce these simpler quantities and then tackle the problem, okay, to actually calculate them. That's what we're doing now. The last one is this, is psi ff, which is B1 ij transposed, of course, C1 ij transposed, of psi ij transposed applied over psi ij in the Vij times C1 ij and B1 ij. Okay. So again, these are just quantities that we have defined prior doing the actual exercise, because eventually these are the quantities or the form that the quantities assume the 2D case with respect to the 3D case that we have seen, that we have eventually to find out or calculate in our exercise. Okay? All right. So that when we are going to see it in the exercise, we don't get frightened. Can I slide? All right. So let's do the actual exercise. Where is it? Oh, I didn't insert it. Yes. Okay, so as you can see here, we have this this element. Oops. We have this 2D beam element, in which you can find the element frame, the inertial frame, x1 and x2 for the 2D case. Then we have the body frame, b1 and b2. Then we have I1, I2 over hat, ij, which is the intermediate frame, which is just co-aligned with respect to the element frame. And therefore, it forms an angle bij with respect to the body frame, okay? And then there is theta I, which is the rigid coordinate describing the orientation of the body frame with respect to the inertial frame. Then we have the element frame here, I1, ij, I2, ij, without the overhead. As you can see, it is collinear. It is parallel to the intermediate frame as per definition, at least as we have seen at the beginning of the deformation process. And then we have all of the nodal quantities, which are, in this case, expressed. You see they have an overhead. So all of them have an overhead. I'm not sure if you notice them, meaning that they are referred to this coordinates. Okay? We have seen that we can use the same element shape functions to encompass a rigid rotation or translation of the element frame. This is the way we introduce the element frame, the intermediate element frame. So it means that we have that x, ij, so the position of a point of the element expressed with respect to the intermediate frame, is equal to psi without any overhead on anything, because they are the usual one. We saw that they can work out pretty well, applied over E overhead ij, where psi ij, okay, I'll try to write it here if I have enough space. So 1 minus xi, zeta, and 0. Then we have 1 minus 3 zeta squared plus 2 zeta to the third, 0 L applied over zeta minus 2 zeta squared minus zeta to the 3, zeta 0, 3 zeta squared minus 2 zeta to the third, 0, and then we have 0 here, and L applied over xi zeta, sorry, to the third minus zeta squared. Okay, this is just a reminder. Now, if you remember, we have that the position of a point within the element expressed with respect to B1, B2, which is a 2 times 1 vector, in this case, was C2 ij, which is a 2 times 2 orientation or rotation matrix applied over X ij, which is a 2 times 1 vector. So I'm just expressing the position of a point from the element intermediate element frame to the body frame. So this matrix here will be a function of what? Beta. Okay? That's it. Well, this, for what we have written so far, is psi ij applied over E, overhead ij, with C2 ij. What is it? So again, it's just a 2D rotation matrix of the angle, yes, of the angle beta. Cosinus of beta ij minus the sinus of beta ij, sinus of beta ij, cosinus of beta ij. Okay, again, this angle here is this one. Okay, so this is a projection or a rotation. Super simple. Okay, so this is the first. But now we have to link this element frame, these quantities which are associated to the intermediate element frame, to the element frame itself via the matrix C1. Next slide. Okay. So we also, oops. That E ij, and this is a 6 times 1 vector, because this is the vector of the nodal quantities associated to the element and refer to the intermediate element frame. So it's 6. If you see, we have 2 nodes, each one having 3 coordinates. So 6. And this is equal to C1 ij applied over QE ij, where QE ij is the vector of the nodal quantities expressed with respect to the body frame. Okay? So C1 ij will be again a matrix, just to be clear. So this relationship here rotates the nodal quantities from the intermediate element frame to the body frame. Okay, so C2, as you can see here, links the position vectors. That's why someone of you said it. So this is a proper rotation matrix. In this case too. This is, well, kind of, because of course has dimension 6 times 6 or n times n in this case. That enforces the same relationship but at nodal quantities level. And of course, in this sense, it will always be a function of beta. So we only have to project basically What I'm saying is that we have to project these quantities over B1, B2, B3. So if you do it, you get that, of course, the relationship is such. And this is for the first node, okay? Why is it so? Well, it's kind of easy if you think about it. So this is a rotation applied over a vector of 3 coordinates associated to the first node. So we have first a translation in the 2 axes, and then we have a rotation. Okay. Of course, the rotation, which is E3 ij overhead, stays the same in the 2 coordinate system. Okay. Oops. So that's why here we have a 1. But why we have this kind of structure that really reminds you of a 2D rotation matrix? Then we will complete it. So this is 2D rotation of angle. What is the rotation angle in this case? So here you have this, and here you have this. So the signs are opposite. Why? Okay, so it's an opposite angle, but why? Instead of passing, we do the opposite. So if we want to do the opposite path, as your colleague was saying here, we're basically applying it to the intermediate to get to the body frame. Here instead, we are applying it to the quantities expressed in the body frame and projecting it to the intermediate frame. So it's basically just having a rotation matrix, but considering an opposite angle. Okay, that's why it's written like so. Of course, the same stuff goes for the second node. So you can expect it to be pretty similar. So it's going to be, oops, cosinus of beta ij, sinus of beta ij, minus sinus beta ij, cosinus beta ij, 1, 0, 0, 0, 0. How about the rest? The rest are all zeros. So 0, 0, 0. Okay. And this is how C1 is actually estimated. Okay. Now we make a simplifying hypothesis because basically it just doesn't add much. Simply, oops. We consider a one element body it means that our body is only constituted of one single element. Okay. So what is the actual consequence, direct consequence of this? The first one is that our connectivity matrix is full of ones, because we have to Booleanly select all of them. There is nothing that merges. Okay? It's only one. It's a matrix. And the second is that QE, which is the vector of the nodal quantities associated to the overall body, Q0I plus B to I QF I how is it, this B? So this is the reference matrix. So it's the matrix which enforces the reference conditions. Basically, it selects the nodal quantities that can actually survive once you impose the boundary conditions, or if you want, the constraints between different elements. Okay, so this is basically tells us which of the overall general vector of possible deformations at the nodes are actually possible for our element. If you remember, when we had the slider, we had the two nodes being simply supported could not undergo two transverse rotations at the ends. Okay, but in our case, if you go and check this, I would say that in theory they are all possible. No? It means that basically this B2 is not appearing in our formulation. And so that R over bar ij, which is QE ij, with N ij being C2 ij, Psi ij, and C1 ij. B1, we don't put it because it's basically just putting a matrix full of ones. Okay. Okay. Now, basically, we have all of the quantities, C1, C2, Psi, to estimate the mass matrix. Okay. Which is something that we will start doing on Monday. Okay. Because I have to leave you with 10 minutes in advance, because I have this presentation to give for the students of the bachelor degree. Okay, do you have any question?